the equation we have, n1 sine theta 1 equals n2 sine theta 2, as I've said, is the general case, and we'll work in pretty much all the situations that we're going to see at A level. I'm going to quickly show you how you can get from this general equation to the special cases. So the first special case we dealt with was the special case where you have light coming from air into a more optically dense medium, and therefore it will refract towards the normal as it slows down. So we have this situation, and how do we get from this equation to the simplified equation that we have for GCSE? So in this situation, n1 equals 1, and n2 equals the refractive index of the material, which we can leave as n. In this case, theta 1 is also the angle of incidence. So theta 1 we could describe as the angle of incidence, and then theta 2 we could describe as the angle of refraction. So then we've got this notation, and if we substitute this notation to this notation into here, what you can see is that you end up with n1 turns into 1, sine I equals n sine R. And you can quickly see that n equals sine I over sine R. That's quite straightforward. So that's our old friend from GCSE, and that's where it comes from. If we look at the alternative situation that we have at GCSE, where we have the light and we're considering critical angle. So the light is incident, it's in the more optically dense medium, so it's going slower, it goes into the air, so n equals 1, so it goes faster, it speeds up, bends away from the normal. So this angle is bigger than this angle. And we can do a similar thing, but we're interested in a special case when the angle of incidence equals the critical angle. So we're not actually interested in this situation as I've drawn it. We're actually interested in the situation when this happens. So rather than us drawing it where it just refracts at any old angle, we're interested in a very specific angle where the angle of incidence causes this to happen. So the angle of incidence causes refraction at 90 degrees, so effectively along the boundary. And at that point onwards, as this angle increases, which means the ray is going in this direction, as this angle increases, then we get total internal reflection. So this angle has a special name, and this angle is C. But in our case, it's theta 1, but theta 1 equals C, so it's a special angle. Now this angle is theta 2, but it equals 90 degrees. We have the same situation where this is n1 this time. So this is n1, and this equals n again. That's the refractive index of the material. And n2 equals 1 because it's air. And remember what I said in the previous video, that you want to keep it, preserve it, so that the thing that happens first is number 1, and the things that happen second is number 2, particularly when you're first getting used to this. So if we then substitute all this into the general equation, I'll just rewrite it quickly. So n1 sine theta 1 equals n2 sine theta 2. But then for this situation, n1 is n, sine theta 1 becomes sine C, and this time n2 is 1, and we have the sine of 90. Now you may know this immediately. You may be saying the sine of 90 is 1, but I can show you that the sine of 90 is 1. So we end up with n sine C equals 1. Therefore, sine C is 1 over n, or n equals 1 over sine C. So again, we can see our old friends from GCSE reappearing as a special case of this more general formula. The final thing I would like to mention, I'm running out of room, running out of paper, is what a refractive index means. So I've used the example of refractive index of 1.4, could choose anything but 1.4. What does a refractive index of 1.4 mean? Well, that means that the light travels 1.4 times faster in a vacuum